Hi, this is Zhen's project progress presentation. Last time I introduced my topic of smart textile and computational music. I mentioned the idea of creating a textile-based interactive system for collaborative music production. It will contain several big-scale interactive fabrics and a projector or AI application that can produce the visual corresponding to user interaction. This time I changed my project structure a little bit to a more experimental, more material exploration and research-oriented. The AI part may be considered at a later stage. So now my proposal will contain two approaches, textile to sound and sound to textile. First, let's look at the textile to sound. When you are interacting with different textile, the perception will be different. My hypothesis is that different textile may have different imagined sound. It may relate it to the texture sound synesthesia. It means that people may associate the certain texture with certain sound. For example, the textile with rough surface may connect to rough sound. And on the other hand, the gesture you are interacting with different textile may also be different. For example, the flexible textile, you may stretch it, and some fuzzy surface, you may stroke it. So the core idea is to embed the imagined sound into the textile, and then I will transform the common gesture that is used to interact with the textile to the mechanism for triggering sound. It's like pressing the key for piano, but the gesture and sound will be new. And this requires some circuit design with sensor to make it happen. So the main manufacturing method I can think of is inkjet printing. The first step is the proof of concept that it's feasible to print conductive ink on the fabric. So I learned how to do the inkjet printing and did some textile experiments. The ink I used was silver conductive ink. Then we need to fill the ink into the cartridge. Initial the machine and put the cartridge into the cartridge container, then clean and set up. Then we send the command of printing. After printing, we need to bake the material, or called curing, for about half an hour. Then we can observe the structure with microscope and measure the conductivity using multimeter. For the first experiment, I tested 3 fabrics. Xinjiang cotton, gauze, and the net woven cotton fabric for bento box. I printed this pattern, the spiral one for simulating the speaker and the other one for testing the circuit. Sadly, they were all not conductive, and as you can see from the microscope image, the conductive ink is not continuous, and the structure is rough, so the interaction between the particles were not good. So in summary, we need the surface to be smoother and with higher density, so that the conductive ink can be linked. Then in the second experiment, I used some high-density fabric and I tested the same pattern. Material I tested were rainbow PVC, high-elastic PU imitated sheepskin, white down jacket high-density cotton, black zhen cord fabric, and the black mirror surface fabricoid. As we can see during the printing, some ink dropped clustered at the textile surface. I think it is because of the hydrophobicity of this textile. This will cause a small problem that the circuit is not continuous. Another problem is when I cure the PVC, it will transform very easily like this. And here is the PVC under microscope I tested. And then is the high elastic PU imitated sheepskin. It succeeds. The performance was good, but we need to print several times to form a thick conductive surface. Then the black zhen cord fabric is also succeeds, but it was not stable and can be conductive when the measuring distance is very short. The black mirror surface fabric coil also succeeds for a circle pattern, but the down jacket high-density cotton failed regarding the conductivity. In summary, from the second experiment, the inkjet printing on fabric will be feasible, and it is better to repeat the printing several times. Also, the type of ink I used performs better for smaller size circuits, and we can try some smaller size the next time. And in the third experiment, I did a more complex pattern simulating the real circuit of the speaker and make the size to become smaller. This time the material I tested was a flat fabric space carton, transparent 0.15mm TPU, and also the material from the previous experiment, black mirror surface carbide and with a PI, which is the usually used for injecting printing for comparison. And let's see the flat fabric space curtain. It was a success, but only at the inner circle. And I measured the resistance is about 24 ohm. For the black mirror surface carbide, it success only at the beginning of the circuit, and we can see from the right side of the picture. So the small circle here, the conductive resistance is 45 ohm. For the polyimide, the performance was very good. The circuit was integrated. The transparent TPU is also conductive at the beginning of the circuit. Finally, I want to report two unstable cases I observed during the experiment. Firstly, in some hydrophobic surface, the droplet may lay down stable as separated dots. So, for some times, occasionally, the dots can be connective. And in that case, we can successfully measure the conductivity. That may explain why in my experiment I succeeded in some small parts. And the next is the parallel knitting surface. There are some small intervals in the parallel knitting surface, and sometimes we can successfully print the ink onto that intervals and forming the conductive surface. But also you can see the areas is rather small. Then I will introduce the next part, sound to textile. I was thinking reversely, what if we can go beyond the existing textile to use advanced manufacturing techniques to develop some new textiles? When I'm doing some research about the textile, I saw the 3D printing textile, which is quite interesting. It seems like we can input something and then there will be a novel shape. That can be utilized in my concept. What if I use sound to generate textile pattern? So the core idea become we input some sound. Then we can use some software like Grasshopper to generate the pattern. We can then use 3D printing to print the pattern out. It is a challenge to discover what kind of structure will make it feel like real textile. I am still learning this, but currently I tried the following method. The first one is from MIT Media Lab called Deflex. The method is adjusting the flow rate of the 3D printer, and if we adjust this parameter to below 50%, we can print a rectangle as normal, and then we can have a flexible feeling. I tried different thickness of rectangles and the flow rate, so the flexibility will be different. The second method is a chainmail, like different kind of lattice connected with each other, but the speed is really slow and it's not like a fabric feeling. Furthermore, I tried the conductive PLA using our 3D printing machine, the DIY one, but unluckily it failed. It's not conductive and easy to be broken. So next, I'm thinking of using inkjet printing as well to apply the circuits on the 3D printing textile surface, and if the structure is very complex. But let's see how far I can go. And that's it. Thank you for listening.